Hello and namaste everyone. I'm Assistant Professor Sunil Rakhal from Institute of Engineering, Tribhuvan University, Nepal. Welcome back to week 5 of our water supply engineering courses. I hope you are all doing well and ready for today's session because this one is particularly important when we talk about water quality in a real world system. So far, we have been discussing sources of water and water demand, but now we are going into what is in the water and more importantly, what should not be. Today, we are diving into lecture 5 of chapter 4, which focuses on 5 key areas: the different types of impurities found in water, suspended, colloidal, and dissolved, and how they affect water quality. Then we'll talk about two major water characteristics, hardness and alkalinity. We will see how these impact treatment process and everyday use. After that, we will get into some numerical problems. Don't worry, I'll walk you through step by step. And finally, we will wrap up with look at living organism uh, commonly found in water like bacteria, protozoa, and algae, and why they matter. Let me quickly walk you through what you will be able to do after today's class. First, you will be able to identify and classify various impurities in water and explain how they impact quality. Second, you will gain a solid understanding of hardness and alkalinity, their definition, types, and interrelationship. Third, you will make sure you are comfortable with the basic numericals related to water hardness and alkalinity. And lastly, you will be able to recognize some of the common microorganisms found in water and why they are important from a treatment and public health point of view. All right, students, now that we have set the stage with our learning objectives, let's move into our core content for today. We'll begin by understanding why water is never really pure, even in nature, and what that means for us as engineers, as a planner. Water. Water is often called the universal solvent. But what does that really mean? It means water has a unique ability to dissolve more substances than almost any other liquids. So, whether it is rainwater falling from the sky or groundwater flowing beneath the earth, it always carries dissolved substances. Even the clearest mountain spring water contains gases, minerals, or even radioactive elements picked up along its journey. Let's classify the sources of these impurities into two main categories: natural sources and human activities. In natural sources, these are substances that dissolves in water as it moves through the air, soil, and rocks. For example, calcium and magnesium. This cause hardness in water. Iron gives water a yellowish tint or even metallic taste. Arsenic, it is a naturally occurring but toxic impurities. Radon or radium is the radioactive element that may be found in deep groundwater. Have any of you ever tasted water with a metallic flavor? That's upon iron. Now, this is where we, as a human, are making things worse. Water pollution from human activities includes fertilizer, pesticides, washing off into the river or shipping into wells, industrial waste and sewage being discharged improperly, household chemicals like detergent and cleaners, These contribute to chemical contamination, making water unsafe for consumption and harder to treat. Because these impurities exist in very small quantities, we use unit like part per million, milligram per liter. 1 ppm is equals to 1 milligram of substances per liter of water. Why do you think we need such a small unit? Because a small amount of arsenic or lead can still be extremely harmful. Let's do a quick comparison uh, between groundwater and surface water. Groundwater moves slowly through soil or rock, whereas surface water exposed to air and runoff. Groundwater have stable, pure, sudden changes in quality parameters, and surface water prone to rapid contaminations. Groundwater have higher in minerals like calcium, magnesium, iron concentration, whereas surface water are lower in minerals. Surface water have a low concentration of minerals and more organic matters in surface water. So groundwater is less exposed to pollutants as compared to surface water, and surface water needs more treatment, especially post rain, because surface water is more exposed to pollutants. Groundwater is generally safer if drawn from deep sealed well, but may be harder to minerals. Even though water may look clean, it contains dissolved substances that affect its taste, hardness, and safety. Understanding these impurities, their sources, and how they affect water quality is essential for managing both public health and infrastructure design. A characteristic of water for domestic usage, water that should be wholesome and should be colorless, odorless, but tasteful. And water should be cool and sparkling, clear, and water should free from biological germs that affects for health and should not corrode the pipe. Water for domestic use should have dissolved oxygen and free from carbolic acid, so that it may remain fresh. It should be free from all objectionable matter. It should be free from poisonous and toxic substances. The domestic water should not contaminate and does not cause waterborne disease. As future engineers, our job is to recognize these and design safe water treatment system accordingly. We will now move into the classification of impurities like suspended, colloidal, and dissolved, and how to deal with them. We will also get into hardness and alkalinity, and I have got a few numericals coming up as well. All right, class, let's move deeper into today's topic, impurities in water. Not just what they are, but how we classify them and how they affect water quality. We will be breaking down into two types of classification according to its characteristic, according to their state or physical form in water. So let's begin. Classification according to a characteristic. We broadly divide impurities into three types. Here, one is physical impurities, second one is chemical impurities, and the third one is bacteriological impurities. In physical impurities, Physical impurities which affect the physical characteristic of water such as color, odor, taste and turbidity. Color, odor and taste is caused due to presence of algae, organic matter, industrial waste, sewage, minerals, microorganisms, etc. And turbidity are caused by the suspended and colloidal matter such as sand, silt, clay, etc. Ever seen a river water after heavy rainfall? That murkiness is turbidity caused by suspended solids. Second one is chemical impurities. Chemical impurities which affect the chemical characteristic of water such as suspended and dissolved solids, pH, hardness, minerals content, chloride, nitrogen, and salt, etc. So these can affect the taste, corrosiveness, and suitability of water for drinking or industrial usage. And third one is bacteriological impurities. Bacteriological impurities refers to the microorganism in water that includes pathogenic bacteria, non-pathogenic organism. Pathogenic bacteria can cause disease like typhoid, cholera, and dysentery. And non-pathogenic organism generally harmless but may contribute to bad odor or taste. So when we say water is potable, it means it's free of these harmful microbes. One thing keep in mind, bacteriological impurities in water causes diseases in human beings, making it unfit for consumption. Bacteriological impurities affect the bacteriological characteristic of water, such as pathogenic and non-pathogenic microorganisms. Now let's classify impurities based on how they exist in water. This helps us understand how to remove them. First one is suspended impurities, and second one is colloidal impurities, and third one is dissolved impurities. Suspended impurities are the dispersion of solid particles that are large enough to be removed by filtration or settling. Suspended impurities are visible or large enough to be settled or filtered. For example, clay, silt, bacteria, algae, organic and inorganic matter. All these are suspended impurities. Most of the suspended impurities are macroscopic and cause turbidity in the water. The concentration of suspended matter in water is measured by turbidity. Suspended impurities also develop color, odor, and taste in water. Some bacteria cause disease. Turbidity unit. Turbidity is measured by turbidity unit like NTU means nephelometric turbidity unit. Turbidity can be removed easily through settling or filtration. And second impurities is colloidal impurities. They are very finely divided dispersion of particles in water which are so small that these cannot be removed by ordinary filters and that are not visible to the naked eyes. These are extremely fine particles, not visible to naked eye. Its size between 1 micron to 1 millimicron. Colloidal particle remains in motion and do not settle. Most of the color of the water is due to colloidal impurities. The size of colloidal particles is 1 micron to 1 millimicron, which I have already told. Colloidal impurities causes most of the color in water, often contribute to taste and odor. This cannot be removed by simple filtration on things. Uh, Please keep in mind, this cannot be removed by simple filtration, but removed by chemical coagulation, sedimentation, filtration. Chemical coagulation means adding alum or lime to clump clump particles to clump particles. And sedimentation and filtration means filtration after coagulation coagulation after coagulation. And third impurities is dissolved impurities. A dissolved substance is own in solution in simple atoms or complex molecular compounds. Dissolved impurities are true solutions like salt or sugar dissolved in water. Physical methods such as filtration, sedimentation, centrifugation cannot remove dissolved substances from water. The removal of dissolved substances requires a phase change from liquid such as distillation, precipitation, adsorption, or extraction. The common type of dissolved impurities are minerals, salt, gases, and chemicals. On things, it cannot be removed by physical means like filtration or settling, but removal requires advanced method like distillation. It means converting water to vapor and reconditioning it. Distillation means converting water to vapor and recondensing it. And precipitation, chemical process to form insoluble particles. And adsorption means using activated carbon or extraction techniques. Why cannot dissolved salt be filtered from water? Because it's chemically bonded at a molecular level. Because of its chemically bonded at molecular level, we cannot dissolved salt be filtered from water. So sand, clay, algae are the examples of suspended particles. Organic colorants uh, are the colloidal particles. Salt minerals are the dissolved particles. And suspended particles gives the turbidity in water and provides color. And colloidal particle directly affect the water. It creates color, odor, taste in water. And while diesel impurities can cause a taste, chemical imbalance, etc. Impurities in water are of many types, and understanding their nature and behavior is crucial. It helps us decide which treatment methods are suitable for clean, safe, and drinkable water. Now that we understand what kind of impurities exist in water, let's dive into a more detailed look at individual constituents like their chemical identities and the problems they cause, and most importantly, how to treat them. We'll go through a comparative table, but I will explain each one clearly, so keep in touch. So this table gives the constituent and their chemical formulas and issue caused by this constituent and treatment method for that constituent. Let's look at this in the four simple columns. One is chemical name or symbols of the constituent, and third one is problem they create, and last one is how we can remove or treat them. First one is turbidity. Turbidity means not a single chemicals caused by suspended impurities. not specified in chemicals term. That means there is no any chemical formula for turbidity. It can cause water appears dirty or cloudy. It can clog pipelines and damage industrial equipment, reduces suitability for most applicants. But turbidity can be removed by coagulation, sedimentation, and filtration. And second one is hardness. Now, hardness is due to mainly due to calcium and magnesium salt expressed as a calcium carbonate, that is CaCO3. It causes its scale building up in heat exchanger, boilers, and pipelines, reduces soft effectiveness. It disrupts processes in industries like textile and dyeing. It can be removed by water softening technique like ion exchange and lime soda treatment. What happens when you shampoo does not foam in hostile tap water? That's hard water. Third one is alkalinity. Alkalinity is the bicarbonates, that means HCO3 minus, and carbonates, that is CO3 minus minus, and hydroxide OH minus is calcium carbonate. It leads to foaming in boilers. It can weaken the boiler's metal. It contributes CO2 in steam, causing corrosion in condensate pipelines. It can be removed or reduced through lime softening, acid dosing, ion exchange, hydrogen zeolite, and dealkalization. Dealkalization. And carbon dioxide, that is CO2, it can cause corrosion in metallic water pipeline and especially affect streamlines and condensate systems. It can be removed via aeration and neutralization with alkaline substances. And another is sulfates. Sulfate SO4 minus minus. It increases the salt content in water, may combine with calcium, forming hard deposits such as calcium sulfate. It is removed by ion exchange, membrane methods, reverse osmosis, electrodialysis, and evaporation. And another is chlorides. It increases the saltiness of water. It leads to corrosion, especially in the presence of high temperature or oxygen. It can be removed by demineralization, reverse osmosis, electrochemical methods, and evaporation. And another is a nitrate. Nitrate is NO3 minus. It adds to solids content but is not usually significant industrially. If high concentration causes methemoglobinemia in infant, useful for control of boiler metal embrittlement. Can removed through demineralization, reverse osmosis, electrodialysis, and evaporation. And another is sodium. The formula is Na plus. Sodium adds to solid content in water, adds to solid content of water. It can be removed through demineralization, reverse osmosis, and electrodialysis, evaporation. And another is silica. The formula is SiO2. Silica can scale in boilers and cooling water system. Insoluble turbine blade deposits due to silica vaporization. It can be removed by hot and warm process, removal by magnesium salts, adsorption by highly basic anion exchange resins. In conjunction with demineralization, can also be removed through reverse osmosis and evaporation. Another is ammonia. Ammonia can cause the corrosion of copper and zinc alloys by formation of complex soluble ion. Can be removed through cation exchange with hydrogen zeolite and also removed by chlorination and deaeration. And another is dissolved solids. Ammonia. The chemical formula of ammonia is NH3. Dissolved solid have no any chemical formula. If the concentration of dissolved solid is high, that are objectionable because of process interference and as a cause of foaming in boilers. Dissolved solids can be reduced or removed by lime softening and cation exchange by hydrogen zeolite, or it can be removed through demineralization, reverse osmosis, by electrolysis, and also dissolved oxygen. Dissolved solid can be removed by evaporation. The last one is suspended solids. Suspended solids deposits in heat exchange equipment, boilers, and water liners. It can be removed through subsidence. Also, it can be removed by filtration, usually preceded by coagulation and settling. So these are the different types of parameters and their causing and their effect and also their treatment methods we present in the table here. So there are a lot of constituent and problem they are caused and the treatment method to reduce the concentration of these particles. We will now proceed to our next session, hardness and alkalinity, where you will learn not just the concept but also how to solve a numerical on it. Now students, tell me, have you ever noticed that soap does not lather well when washing hands or clothes with water from some source? That's because of hardness. So hardness is the characteristic of water that resists the formation of lather with soap. Hardness is the characteristic of water that prevents the formation of sufficient lather foam with soap. Hardness is caused by presence of bicarbonate, sulfate, chlorides, and nitrates of calcium, magnesium, and strontium. Hard water forms precipitate due to formation of insoluble soaps, calcium stearate, and magnesium stearate. Hard water forms precipitate due to formation of insoluble soap. Hardness is caused by dissolved salt of bicarbonate, sulfates, chlorides, nitrates of calcium, magnesium, and strontium. These ion reacts with soap to form insoluble scum like calcium stearate, which fluids or settles instead of forming foam. Whereas alkalinity of water is its capacity to neutralize a standard solution of acid. It is caused due to presence of bicarbonate, carbonate, and hydroxide. Alkalinity of water is its capacity to neutralize a standard solution of acid. The effect of hardness consumes more soap foams scale in boilers. It modifies color in the drying industries. It causes corrosion and incrustation of pipes. It makes food tasteless. These are the effect of varnish. Now let's break down into three types. One is carbonate or temporary hardness. Second one is non-carbonate or permanent hardness. And third one is total hardness. So carbonate hardness is also called temporary hardness. So hardness caused by presence of bicarbonate of calcium, magnesium and strontium. Strontium is known as carbonate hardness. Once again, hardness caused by the presence of bicarbonate of calcium, magnesium and strontium is known as carbonate hardness. Carbonate hardness also called temporary hardness, called temporary because it disappears with simple heating. Boiling precipitates the bicarbonates as insoluble carbonates. Another is non-carbonate or permanent hardness. Non-carbonate hardness caused by the presence of sulfate, chlorides and nitrates of calcium, magnesium and strontium. It is caused by the presence of sulfates, chlorides and nitrates of calcium, magnesium and strontium. It cannot be removed by simple boiling, so called as permanent hardness. It can be removed by lime soda and zeolite method. It cannot be removed by boiling, requires chemical methods, that is lime soda process, zeolite, that means ion exchange method. This is common in many industrial water sources. And last one is total hardness. Total hardness is the summation of carbonate and non-carbonate hardness. CS meaning here is carbonate hardness and NCS is the non-carbonate hardness. So the sum of carbonate hardness and non-carbonate hardness is gives the total hardness. So now I'm going to a quick summary of this. Carbonate means temporary hardness is caused by bicarbonate of calcium, magnesium. It can be removed by boiling. And permanent hardness is also called non-carbonate hardness caused by sulfate, chlorides, nitrates of calcium, magnesium and strontium. It cannot be removed by boiling. It can be removed by lime soda or zeolite. And total hardness is the summation of the carbonate hardness and the non-carbonate hardness. Remember, we already saw how hardness affect industry, shop usage and even pipe safety. Understanding the type of hardness helps in choosing the correct treatment methods. Let's now continue the class session for water supply engineering chapter 4, quality of water, focusing on types of alkalinity. Before going into this, we conclude the temporary and permanent hardness. Conclude the concept of temporary and permanent hardness. Total hardness is the sum of carbonate hardness and non-carbonate hardness. Temporary hardness is caused by the presence of bicarbonate of calcium, magnesium and strontium. Permanent hardness is caused by the presence of sulfates, chlorides and nitrates of calcium, magnesium and strontium. It can be removed by boiling and water, and permanent hardness can be removed by the lime soda and zeolite method. Temporary hardness is also known as carbonate hardness, whereas permanent hardness is also known as non-carbonate hardness. One thing Please keep in mind, unit of hardness is milligram per liter or ppm or degree Clark, and 1 degree Clark is equals to 14.14 milligram per liter. 1 degree Clark is equals to 14.14 milligram per liter. The major form of alkalinity is the bicarbonate alkalinity. Alkalinity is the capacity of water to neutralize acid. They represent the buffering power of water. So alkalinity represent the buffering power of water. Alkalinity is not the same as pH. pH tells us how acidic or basic water is. Alkalinity tells us how much acid the water can absorb without changing pH much. There are many sources of alkalinity. The major contributors are bicarbonates, carbonates, and hydroxide. These substances act as a buffer that resists acidification. The carbonate alkalinity and bicarbonate alkalinity, or carbonate alkalinity and hydroxide alkalinity, can exist together, but bicarbonate alkalinity and hydroxide alkalinity do not exist together. Alkalinity is also measured in milligram per liter or ppm as CaCO3. The alkalinity of water is expressed in ppm or milligram per liter as calcium carbonate CaCO3. And the formula for carbonate alkalinity in milligram per liter as CaCO3 is equals to iron concentration in milligram per liter times equivalent weight of CaCO3 divided by equivalent weight of iron. Once again, carbonate alkalinity in milligram per liter as CaCO3 is equals to iron concentration in milligram per liter times equivalent weight of CaCO3 divided by equivalent weight of iron. Total alkalinity is the sum of carbonate alkalinity and bicarbonate alkalinity, or total alkalinity is the sum of carbonate alkalinity and hydroxide alkalinity. But hydroxide alkalinity and bicarbonate alkalinity cannot exist together. Please keep in mind, carbonate alkalinity, bicarbonate alkalinity and hydroxide alkalinity do not exist together. Here are the relationship between hardness and alkalinity. If the concentration of hardness, or if the level of total hardness is greater than total alkalinity, the carbonate hardness is equals to total alkalinity, and non-carbonate hardness is equals to total hardness minus carbonate hardness, and that is equals to total hardness minus total alkalinity. And if the total hardness is less than or equal to total alkalinity, then carbonate hardness is equals to total hardness and non-carbonate hardness is 0, because non-carbonate hardness is equals to total hardness minus carbonate hardness, and the carbonate hardness is equals to total hardness. So non-carbonate hardness is equals to 0. This is the relationship between hardness and alkalinity. If your water has only bicarbonate alkalinity only, If your water has carbonate plus bicarbonate, both exist. If your water has carbonate and hydroxide, both exist. But if your water has hydroxide and bicarbonate, that is not possible. This is especially important in determining scale formation and treatment method. TH is the total hardness, Ta is the total alkalinity, TH is the carbonate hardness, and NCH is the non-carbonate hardness. When you know both total hardness and total alkalinity, you can decide the treatment process like lime soda versus ion exchange, predict whether the water is scaling or corrosive, control industrial problem in boilers and cooling systems. So let's now move into a very important and practical segment of today's class, the numericals on hardness and alkalinity, which is frequently asked and used in water treatment planning. And the given question is the analysis of water from a well showed the following results in milligram per liter. Find the total hardness, carbonate hardness, and non-carbonate hardness. The concentration of Ca++ is equals to 65 milligram per liter. The concentration of Mg++ is equals to 51, and the concentration of Na plus is equals to 101.5, and the concentration of K is equals to 21.5, and the concentration of HCO3 minus is equals to 248, and the concentration of SO4 minus is equals to 221.8, and the concentration of Cl minus is given by 79.2. We have hardness in milligram per liter is CaCO3. The formula of hardness, total hardness, is CaCO3 is equals to ion concentration in milligram per liter times equivalent weight of CaCO3 divided by equivalent weight of ion. So the question gives us the ion concentrations, that is Ca++ ion and Mg++ ion. These Ca++ and Mg++ ions are the hardness component. Hardness, total hardness is due to calcium ion and magnesium ion only. Here strontium ion is not given in the questions. So total hardness is the hardness due to calcium ion and magnesium ion only. So the hardness due to calcium ion means the ion concentration is 65 times equivalent weight of CaCO3. The equivalent weight of CaCO3 is 50 divided by equivalent weight of ion, that is equivalent weight of Ca++. Equivalent weight of Ca++ is equals to 20. So 65 into 50 divided by 20. So 50 is the equivalent weight of CaCO3 plus. Hardness is also due to magnesium plus ion. That's why magnesium ion concentration times equivalent weight of CaCO3 divided by equivalent weight of ion. That means equivalent weight of magnesium ion. So the ion concentration is given by 51, and the equivalent weight of CaCO3 is 50 divided by equivalent weight of ion. That means equivalent weight of Mg++. Equivalent weight of Mg++ is equals to 12.2. So divided by 12.2. So from this The total hardness is equals to 371.52 milligram per liter is calcium carbonate. For calculating non-carbonate hardness, since there is no carbonate and hydroxide alkalinity, means there is no CO3 minus minus, that is carbonate, and there is no OH minus ion, that means there is no carbonate hydroxide alkalinity. If there is no any carbonate and hydroxide alkalinity, that means total alkalinity is equals to bicarbonate alkalinity only, because only HCO3 minus is present in this water sample. So the total alkalinity is equals to bicarbonate alkalinity only. The total alkalinity in milligram per liter is CaCO3 is equals to HCO3 minus concentration into equivalent weight of CaCO3 divided by equivalent weight of ion, that means equivalent weight of HCO3 minus. Total alkalinity is the milligram per liter as CaCO3 is equals to ion concentration HCO3 concentration, that is given in the question, is equals to 248, and the equivalent weight of CaCO3 is 50 divided by equivalent weight of HCO3. Equivalent weight of HCO3 minus is equals to 61. So from this, total alkalinity is equals to 203.278 milligram per liter as CaCO3. Here, if we compare the total hardness and total alkalinity, here total hardness is greater than total alkalinity. Therefore, carbonate hardness is equals to total alkalinity. So carbonate hardness is equals to 203.278 milligram per liter HCaCO3, and the non-carbonate hardness, the formula of non-carbonate hardness is total hardness minus carbonate hardness. Total hardness is 371.52 minus carbonate hardness is 203.278, and from these 168.24 milligram per liter is CaCO3, that is non-carbonate hardness. So by this we can calculate the non-carbonate hardness by using this formula, by using this technique. So we have another questions for total hardness and alkalinity. This is the very insightful numericals examples. This one will test your conceptual clarity on hardness, alkalinity, and ion concentration in water. So the questions is the total hardness value obtained from the analysis of a water sample is found to be 230 milligram per liter. The analysis further showed that the hardness has been caused by calcium and magnesium ions only, and their concentrations are numerically same. If the value of carbonate hardness is 90 milligram per liter and alkalinity in water is caused by bicarbonate ion only, calculate the following: the value of non-carbonate hardness, the concentration of calcium and magnesium ion, and the concentration of bicarbonate ions. The solution, we have the hardness in milligram per liter as CaCO3 is equals to ion concentration into equivalent weight of CaCO3 divided by equivalent weight of ion. So the total hardness is given by 230 milligram per liter, and the carbonate hardness is 90 milligram per liter. So the non-carbonate hardness is the formula of non-carbonate hardness is the total hardness minus carbonate hardness. The total hardness is 230 minus carbonate hardness is 90. So 140 milligram per liter is the non-carbonate hardness. Let P be the concentration of calcium and magnesium ion. P be the concentration of calcium and magnesium ion. The total hardness is caused by calcium and magnesium ion here. So P is the concentration of calcium and magnesium. Question tells us the concentration of calcium and magnesium ion is same. So the total hardness is due to calcium and magnesium. So the total hardness is equal to hardness due to calcium. That means concentration of ion, that is P, times equivalent weight of CaSO3, that is 50, divided by equivalent weight of ion, that means equivalent weight of calcium, that means 20, plus hardness is due to magnesium ion, that means concentration of magnesium is P and equivalent weight of CaSO3 is 50, divided by equivalent weight of magnesium ion is equals to 12.2, and it gives the total hardness, that is equals to 230, that is given in questions. From here we can calculate the value of P. So P is equals to 34.85 milligram per liter. So the concentration of calcium and magnesium ions in this water sample be 34.85 milligram per liter. Since non-carbonate hardness is greater than 0, we already determined the value of non-carbonate hardness, that is greater than 0. So total hardness is greater than total alkalinity. That's why total alkalinity is equals to carbonate hardness, that is equals to 90 milligram per liter. And bicarbonate alkalinity is equals to total alkalinity, that is equals to 90 milligram per liter. So we have the formula: bicarbonate alkalinity is equals to HCO3 minus concentration divided by 1.22, but we have HCO3 minus concentration. That means in this formula we have to determine HCO3 minus concentration, because bicarbonate alkalinity we have already determined, and from here we calculate HCO3 minus concentration. That means HCO3 minus concentration is equals to bicarbonate alkalinity times 1.22. So the bicarbonate alkalinity is 90, and 90 times 1.22 gives the concentration of HCO3 minus, that is 109.80. These examples illustrate how chemical equivalence and proportionality help in determining hidden concentration from just a few test values, a skill crucial in water quality labs and treatment plant designs. So next we will move to the biological aspect of water quality, that is living organism in water and their effects. Water is teeming with various living organisms, which can range from tiny microorganisms to larger plant and animals. They can be harmful or non-harmful, and understanding their impact is crucial for water quality management. There are some characteristics of living organism in waters. They can be unicellular, like single-celled organisms, or multicellular. They can be microscopic, too small to see with the naked eye, or macroscopic, large enough to be visible. These organisms can neither either be beneficial or harmful depending on their types and concentration. Algae, bacteria, viruses, and worms exist in the water as a living organism. And what is algae? Algae are aquatic plants that can range from microscopic single-celled organism to larger forms. They grow in surface water, particularly when the water contains nutrients such as phosphorus, often from domestic runoff or industrial pollutions. They derive energy from inorganic substances like gases and salts and sunlight. It is self-nourishing, means algae are capable of producing their own food through photosynthesis. Excessive algae growth can cause problems such as taste and odor issue in water, clogging of filter in water treatment plants, formation of nuisance simple formation of nuisance slime growths on intake pipes and equipments. Algae can be controlled using chemicals like copper sulfate or chlorine. And what is bacteria? Bacteria are microscopic single cell organisms that can multiply through simple division. It is universally distributed. They are found everywhere on surface, in air, and of course in water. Helpful bacteria assist in decomposition of organic materials, but harmful bacteria can cause serious diseases like typhoid, dysentery, cholera, gastroenteritis, etc. Certain non-harmful bacteria like sulfur bacteria can produce hydrogen sulfide leading to unpleasant odors. Crenothrix iron bacteria can create stains, disagreeable taste and odor. These are the basic classification of bacteria based on oxygen need, shape, life process. Based on the oxygen need, the bacteria are classified as aerobic bacteria, anaerobic bacteria, and facultative bacteria. And based on the shape, Kochi bacteria, Bacilla bacteria, and Spirilla bacteria. Based on their life process, saprophytic bacteria and parasitic bacteria. These are the classification of bacteria based on oxygen need, shape and life process. Aerobic bacteria needs oxygen to survive. Anaerobic bacteria survive without taking oxygen. These are the shape of the bacteria, a sphere shape, a rod-like shape, and spiral shape. So this figure gives the different shape of the bacteria. And another subtopic is viruses. Viruses are ultra microscopic infectious agent that can infect both plant and animal cells. They pose a significant concern in water supply system due to their disease causing potential and resistance to detection. The main characteristic of viruses in water is it is it have no metabolic system. So viruses lack the biochemical machinery for metabolism and reproduction. Therefore, they need a host cell to multiply. They can survive for several weeks in the atmosphere, particularly at a temperature below 15 degrees centigrade and ranging from 10 to 500 millimicrons in diameter, making them much smaller than bacteria. Viruses that may be carried by water include the hepatitis and poliovirus. They are very difficult to test for. Usually large amount of water have to be tested by using very sophisticated method. Viruses can be inactivated by disinfection. The sum of the viruses are poliovirus, hepatitis type A virus. The poliovirus is polio, polio and hepatitis type virus are the main type of virus, and another virus is enterovirus, ecovirus. So different type of virus: HIV, hepatitis B, Ebola virus, influenza, rabies virus, rotavirus, herpes virus. These are the different types of virus. And we move on to the another subtopic, that is worms. Worms or helminthes are parasitic organisms that can live in or be transmitted through contaminated water sources. They represent a significant public health threat, especially in areas with poor sanitation. Flatworms are two groups. Mainly, worms are classified into roundworms, that is, nematodes and flatworms. Hookworms and ascarids are example of roundworms. Flatworms are two groups: tapeworms or cestodes and flukes or nematodes. Ascaris and guinea worms are disease associated with nematodes. Nematodes worm, while schistosomiasis is caused by trematode flatworms. Infection is either through the injection of worms or penetration through the skin. The worms and eggs are transmitted via consumption of contaminated water or vegetables or body contact with polluted water. They can be removed by controlling turbidity through effective coagulation and filtration. These are the classification of worms. Worms is classified as flat worms and round worms. Flat worms, the tapeworms and schistosomiasis trematodes are the examples of flat worms, and ascariasis is the round worms. So living organism in water can have a significant impact on water quality. Understanding how to control and manage their presence is vital to ensuring safe drinking water and maintaining water infrastructures. Whether it's algae causing taste issue or viruses leading to potential diseases, proper disinfection, filtration, and monitoring are key strategies in maintaining the water safety. And finally, these are the work cited. Hope this breakdown helped clarify the role of living organism in water and their impacts. And thank you for this session.